that should be the total moment divided by the distance, right? Which is the force arm. And that means because MA and MB, they have the same direction, which means that MB is just MA plus MB divided by L. And that, of course, equals to RA. Right? And after that, we can just start formulating the governing equation. Because now we have the correct free body diagram to consider. And which means if you consider this, let's not forget about our positive directions. Even so, it's very obvious, but it never hurt to copy it. So this is going to be our X and this is going to be our Y. Like this, which means our X and Y are like this. And you have the forces P here. This is your RA. You have M moment MA here. And right here, you also have P. What about internal moment? What direction is the internal moment? Clockwise? Counterclockwise.
Counterclockwise.
Yes, very good. Counterclockwise. So this is M internal. Do we have shear?
Yes.
Yes, right? Of course. And in this case, what's the direction of shear?
Up.
Goes up, right? And so this is your shear. And that's the complete free body diagram. Once you arrive at this step, then everything else will be just relatively easy. And then we can just write down the summation of moment to be 0. You can take this at the support A, and let's assume because everything is clockwise, so let's assume clockwise to be 0, to be positive. And when we do that, the moment equilibrium becomes, you have MA, and P is also positive, right? So it's MA plus P times Y, that's positive. But the moment produced by the reaction is negative, and the shear is also negative. So that's minus MA plus MB over L times X. Right? And this will be this minus internal moment. Must be 0. Right? Then we have everything.
So, Professor, we're not taking moment at support A, right?
We already have support A here. Support A is MA plus MB divided by L. That's also the shear. Right?
Yeah.
You only consider one of them, correct? All right. So now, because M internal is negative EI times Y double prime, so we will have this final expression, which is EI Y double prime plus PY minus MA plus MB over L. Actually, well, we can write it either way, plus MA to be 0. And you can move this to the other side to make it to be this. Y double prime plus K squared times Y equals EIL over MA plus MB times X plus minus MA over EI, like this. And the general solution, which is a summation of particular solution and complementary solution, it can be written like this. Y equals YP plus YC, which can be written as, let me actually following the same order that I want to give you, like this. YC plus YP. The first one is sine and cosine, and that is A times sine KX plus B times cosine KX YC plus MA plus MB over EIL K squared. Of course, they can be simplified by P times X minus MA over EI over K squared. Now, it's always advantageous to simplify your expression because K squared is P over EI, right? So when you see EI times K squared, what does that mean? That means it's P, right? Which means that you may want to write this as this, even so it may only make a slight difference, but it reduces the possibilities for you to make mistakes when you copy expressions from one place to another. So B times cosine KX plus, this will become PL MA plus MB times X minus MA over just P. So I will always recommend you to work with this expression, not the one before. This is easier to work with. Okay, and we will leave the, we will stop here. Okay. And if you have questions, you can stay. I will stay online until maybe 9:40. Otherwise, I will see you next week.
Professor, I have a question.
Please.
At the bottom of page 48, you have max deflection is less than delta. I was wondering what delta was.
Delta is a design value.
Okay.
Like the sigma y is the material strength, and delta means that's your design criteria. And Y max is the case when you consider certain low combinations.
Okay, thank you.
Welcome.
Thank you, Professor.
You're welcome. Have a good night.
Thank you, Professor.
Professor, have a good night. Thank you.
Good night.
Thank you.
Professor, I have one quick question regarding the homework submission.
Yeah.
Do you want us to like email them to you, or do you have a spot on Blackboard for them?
Right now, I think you can just email me.
Just email to you? Okay, awesome. Thank you.
Yep.
All right, have a good night.
Sure.
Good night, Professor.
Good night.
Professor, can you cover again the last step on example 10 when P approaches infinity? What happens to the maximum moment?
The last step. Which one?
Keep going.
Here?
Yeah, no, keep going. I think it's one more page, maybe. Yeah, one more page.
One more.
Well, we're talking about the maximum moment.
Okay. Maximum.
One more. So yeah.
Yeah.
Okay, I think at the bottom, the sort of very simplified version. Like I was kind of confused with what happens when P approaches infinity. If P approaches P, I understand that it becomes it becomes, well, the expression approaches infinity. But if P approaches infinity, what happens? Like, doesn't M just become zero? Like,
okay, that's more like a philosophical question in structural stability. But let's get everything clarified here. And so if we come back to this, you remember we start with this low deflection curve, right? So you have the loading and you have positive deflection and a negative deflection, something like this, correct? That's where we started. And I said that when we start, I mean, finding the buckling low of any kind of structures under our consideration, we started by thinking about that the load will start increase from 0 and all the way to here. Yeah. Now, there are lots of things that in structural stability that we can do. And in this particular approach, or my approach, we are interested in finding that what will be the level of force that would let the structure to fail without reaching its material strength. Because if it's a ductile material, you understand that there's a sigma y here, right?
Yeah.
And suppose it's a concrete, you may call it as F prime C. Somewhere here, of course, F prime C must be much lower than sigma y because concrete is considered much weaker.
Yeah.
Still. So you can imagine that is somewhere there's a F prime C here for concrete. The purpose for structural analysis or stability is to recognize that material strength is here. It's a material strength. Limit. And that's not confused with the concrete. So just consider steel. This way you have only value. Okay, that's why it's easier. And there's a possibility that structure will fail. Not because it reaches its limit, it's because it reaches another point. And this point is somewhere here. Turns out this point is PCR. Right? For PCR, of course, you can calculate, find the sigma CR. Right? And here, of course, we use stress. So here, to be accurate, I should not call this sigma y. I should call this py. Right?
Yep.
You call this py, and then there's no stress here. Everything is force. Okay, like this. Now, so by defining this PCR, we assume that your loading, we're only interested in this region. We're only interested in this region, which is here.
Yeah.
Because we want to make sure, do everything we can to make sure that you are aware of this one and try to modify your design such that your structure will not fail all of a sudden because you know the material strength. However, in this case, the material will not be able to reach the strength because there's another failure mode.
Yeah.
Right? What happens to the case when P becomes infinity? If you look at this diagram, where's P equals infinity?
It's above PCR.
Oh, so it's way above, right?
Yeah.
It's way above, far away, somewhere here. And if it's infinity, of course, we cannot even consider that, right? So with this big picture in mind, you will know that in order for the loading, for your cross-section to be loaded up to P approach to infinity, you first of all, you have to pass critical load.
Yeah.
Secondly, you have to pass material strength. Do you think that's possible?
Makes sense. Yeah. As soon as you draw the graph, I was like, yeah.
Right now, is that clear now? So you know it's no way, right? In fact, realistically speaking, material strength is even your best hope. Why material strength is best hope? Because when we consider Py, we assume that the cross-section had uniform strength, sigma y. But the argument I made earlier in this class is there's always material imperfection. So in most cases, your cross-section will not be able to take up to Py. So when we consider Py, that means everything is perfect. You have perfect material, perfect geometry. What is the issue with critical load is just to indicate that because there's no such thing is called perfect. Therefore, structure will fail. You will not be able to reach Py because you assume perfectly straight column. You know what? In buckling, the column is not going to be straight. And also because of materials imperfection, because of residual stress, you're not going to deal with perfect straight column and let load to load it all the way to Py.
Makes sense.